Let us obtain the equivalent focal length of combination of thin lenses placed in contact. Now see, here there are two lenses A and B, and their focal lengths are f1 and f2. Okay, and they are placed in contact with each other. This is the object O, okay, which is placed at point say O beyond the focus of the first lens. So this object O is placed beyond the focus of the first lens. Now see, if this first lens is only there, if the second lens is absent, then the image formed by the first lens would be at I1. Now try to understand, if second lens is then say introduced, okay, second lens is introduced, then instead of I1 the image is obtained at this point say I. It means that the image which is produced here by the first lens, that is lens A, will behave as virtual object for the second lens, and its final image is obtained at point I. Okay. Now we consider that initially the object which is placed here at O is at distance u from the first lens, and the image which is produced by the first lens, try to understand, first lens is at I1, so image distance is v1, and this image behaves as an object for the second lens, so object distance for the second lens would be v1, and finally the image is produced at point I, so the image distance for the second lens, that is B, will be v from the second lens. Okay, so by considering this fact, if you apply the lens formula for the first lens, then 1 upon v minus 1 upon u is equal to 1 upon f, this is the general formula, and for the first lens, for lens A, this will be 1 upon v1 minus 1 upon u is equal to 1 upon f1, and for the second lens, as image distance will become v1, image distance will become v, image distance will be v only, okay, and object distance will be v1, because I1 behaves as intermediate virtual object for the second lens. Here you can see again the object distance for the second lens would be v1 and image distance would be v. So the equation for the second lens can be written as 1 upon f2 is equal to 1 upon v minus 1 upon v1. Now just we have to add the two equations which we have obtained. This equation and this equation both are added. Then you can see that 1 upon v1 will be cancelled out. So you will have 1 upon v minus 1 upon u is equal to 1 upon f1 plus 1 upon f2. And as you know, 1 upon v minus 1 upon u is nothing but the focal length of the combination of the two lenses, or we can say equivalent focal length of combination of two lenses, we can say, or we can take 1 upon v minus 1 upon u as 1 upon f, where f is the equivalent focal length of the combination of two lenses. So the equation goes 1 upon f is equal to 1 upon f1 plus 1 upon f2. If there are n such lenses which are there in contact, then equivalent focal length f of n such lenses can be 1 upon f is equal to 1 upon f1 plus 1 upon f2 up to 1 upon fn. You can extend up to n lenses. Okay. Now from this discussion we can go for the equation of power for the combination of lens. Now see, power is 1 upon f. Okay, as you know, inverse of focal length is power. So equivalent power of combination of n lenses can be P is equal to P1 plus P2 up to Pn. Here 1 upon f is taken as equivalent power of the combination of lens, which is equal to the sum of individual power of different lenses in contact. Okay. Now we talk about the equation of magnification of combination of lenses. Now see, same figure but some notations are made different. Okay, initially the object is at point O, object distance is u from the first lens. Okay, its image would be formed at I prime, or we can say I prime is the image formed by the first lens when the object is at O. Okay, so I prime behaves as the virtual object for the second lens, and final image is formed at point I. Intermediate image is at distance v prime from this combination of lens. Okay, these lenses are very thin. Okay, so you take the distance from first lens or second lens, it does not make any difference. That is why it is taken from the, we can say, combination of lens, because these lenses are thin, very thin. Okay, and the final image is at I, its image distance is v from the combination of lens. Okay, so in this figure it is denoted OP. OP is the object distance. Okay, PI prime is v prime, that is image distances, that is intermediate images at distance v prime. Final image is having its distance pi is equal to v. Okay, now from this figure we can see that for the first lens the magnification m1 can be v prime upon u, image distance upon object distance, and finally for the second lens m2 is v upon v prime. Now finally, if you want to find the magnification of combination is nothing but v upon u, and because the lens is having the magnification image distance upon object distance v upon u, so v upon u is kept as it is, and we are multiplying and dividing by v prime. Just see, v upon u is kept as it is, you are multiplying by v prime and dividing also by v prime. So v upon v prime is nothing but magnification of second, and v prime upon u is the magnification of first. So we can say that the magnification m is nothing but the product of the magnification of two lenses. And if there are n such lenses in contact, okay, then final magnification will be the magnification of, or rather product of magnification of individual lens. Okay, now we shall talk about the prism. Okay, obtain the relation between incident angle, emergence angle, prism angle and deviation angle. Now first of all we consider or we understand the refraction by the prism. This is a triangular prism. Okay, we can say equilateral prism it is. This PQ is the incident ray. This dotted line shows the normal drawn at a point of incidence. So this angle with the perpendicular drawn at a point of incidence, this particular angle is angle of incidence, that is I. Now as this ray goes from rarer medium to denser medium, then it has to bend towards the normal. So this is the refracted ray, which is making the angle of refraction R1 with the perpendicular. Now this refracted ray will fall on this second side, that is AC side of the prism, and it goes from now denser medium to the rarer medium. Okay, so what will happen? It will go away from the normal. So this is the incident ray for the AC phase. Okay, normal drawn at a point of incidence is the dotted line. This ray when goes from prism to air, or we can say denser to rarer medium, then it will go away from the normal. So this angle which is made by the emergent ray, the ray which is coming out from the prism is an emergent ray with the perpendicular. The angle made by emergent ray with the perpendicular is nothing but angle of emergence. Okay, so all these angles I have shown. This is angle of incidence. Okay, again I am showing this is angle of incidence, this is angle of refraction for the first phase, that is AB phase of the prism. Then R2 becomes, this R2 becomes the angle of incidence for this AC phase. Okay, and the ray goes from denser medium to rarer medium. So this is the emergent ray which makes an angle E with the normal drawn at a point of incidence at the AC phase of the prism. Okay, so these are angle of incidence and angle of emergence. Okay, which I have shown. Angle of incidence, angle of emergence, these are different angles. At this incident phase, this becomes the angle of refraction, while the phase from where the ray is emerging out, or emergent phase we can say, this angle is considered to be angle of incidence for this AC phase. Now try to understand, if this ray, if this emergent ray is extended in backward direction, in this direction, and this incident ray is extended in forward direction, then there is an angle between this incident ray and this emergent ray. You can see this angle. Okay, again just you can see. Okay, this angle which is there between this incident ray and this emergent ray, this angle is nothing but angle of deviation, which is denoted by delta. Okay, so this is all about the figure. Now this figure, the different things are explained here. Now you can consider the quadrilateral AQLR. You can see this quadrilateral AQLR. Okay, I am showing it here. Quadrilateral A, Q, L and R. Okay, this is the point L. Okay, A, Q, L, R. Okay, so this quadrilateral I am talking. In this quadrilateral you can see angle AQL and angle ARL. These two angles are of 90 degree. Angle AQL and angle ARL. Again, this is angle, or this is point L, AQL and ARL of 90 degree. Now in quadrilateral, the sum of four angles is equal to 360. So these two angles are of 90 degree. Then rest of the two angles, that is angle A and angle QLR, will be 180, because this 90 and this 90, that is 180 has gone out of 360. So rest of the two angles, that is angle of prism, that is angle A, this is called angle of prism, that is angle A, and angle QLR will give you 180. So you can see, okay, angle A and QLR is equal to 180. Okay, now consider the triangle QLR. Just go through the figure again. You have to take the angle QLR. Okay, triangle QLR, this is L. Okay, QLR you can see. this triangle is taken into consideration, that is triangle QLR. Now in this triangle you can see that the sum of three angles is 180. So you can write this way, okay, in this triangle QLR, this is L, okay. You can see the two angles R1 and R2. So angle R1 plus angle R2 plus QLR. QLR is equal to 180. Because as you know, the sum of all the three angles in the triangle is 180. So angle R1 plus angle R2 plus this QLR is equal to 180. So you can see this here, okay, in triangle QLR, R1 plus R2 plus QLR is equal to 180. Now see, there are two equations for which their right hand sides are 180. This is 180, this is 180. So we are comparing these two equations. So R1 plus R2 plus QLR is equal to A plus QLR. You can see that is compared here. This QLR can be cancelled out. Okay. So R1 plus R2 is equal to a very important result. R1 plus R2 is equal to angle of prism. Okay. Now deviation angle, you can see that this deviation angle can be written as, now see, that is shown here in this figure. See, properly you just look at this, okay. Here if you consider angle delta 1 and here if you consider angle delta 2, then in this particular triangle MQR, you can see this triangle MQR, this angle delta is the exterior angle of this triangle MQR, and as you know that sum of interior opposite angles are delta 1 and delta 2. So we can say exterior angle delta is equal to interior opposite angle and its sum, that is delta 1 plus delta 2, that is sum of interior opposite angle. So here that is shown in the theory, okay, that delta is equal to delta 1 plus delta 2, okay, that is shown here, delta is equal to delta 1 plus delta 2. Okay, now you can see angle DQR. Angle DQR is DQL minus RQL, that is I minus R1. Or we can say the another way also. You can see from the figure, okay, closely look at this figure. This is delta 1, again I am showing it to you, okay. You can see easily this is delta 1. Now these two are vertically opposite angle, just see it. Okay, so these two are vertically opposite angle. So you can see I is equal to delta 1 plus R1. So delta 1 can be written as I minus R1. Similarly, here also you can see these are vertically opposite angle. You can see there is a cross. Okay. So angle of emergence E is equal to sum of these two angles, that is delta 2 plus R2, or we can say E is equal to delta 2 plus R2. So R2 can be written as R2 is equal to E minus delta 2. Okay, R2 is equal to E minus delta 2. Okay, so R1 is nothing but I minus delta 1, okay, and R2 is E minus delta 2. So we got the value of R1 and R2, and instead of this R1 and R2, now you can place these two values in the equation which we have obtained, okay. So delta 1 is I minus R1, delta 2 is E minus R2. These two values we have obtained of delta 1 and delta 2, and these two values can be placed here in this fourth equation instead of delta 1 and delta 2. So you will get easily delta is equal to I minus R1 plus E minus R2. Take these two together and take minus sign common. So minus R1 plus R2 it becomes, and R1 plus R2 is nothing but angle of prism. So instead of R1 plus R2 we write A. So you will get I plus E is equal to A plus delta. Very important equation for the refraction by prism, okay.